Good. So this is our last topic in our course outline, and it has to do with electricity. And before we can actually uh, understand, electricity, at least have a basic understanding of it, we have to, analyze what happens at the atomic level of, various materials, right? And there's a little explanation here telling you that what really happens is that um, the outer electrons, in particular, of certain elements, they tend to be not so strongly bound to the nucleus, right? And sometimes the application of uh, an electrical force, but we don't talk about what that is just now, can cause an electron to move over from one atom to the next, right? And when that happens, what happens sometimes now is that, well, a void is created in one atom. Now, what that will mean is that an electron can be pulled from another atom to fill that void and so on, right? And that can actually create what we will call an electric current or a flow of electrons, right? Uh, so just a basic understanding of what is going on at the atomic level can help us to understand how is it that electrons end up flowing, right? And as we go on, you're going to see some materials, uh, well, this flow of electrons is easier, while others, no. There's some difficulty because of the type of bonding, right? I'm not going to get into the chemistry so much, right? For example, let's talk about conductors. There's a term we apply to materials that allow this flow of electrons that we're talking about, right? Among atoms. We call them conductors. So when there's this little force that drives electrons from atom to atom, well, certain materials, which you see the heading here, we're talking about conductors, or I should say good conductors, right? Will tend to facilitate this flow better because of the structure of the atoms, right? I think in chemistry they call it metallic bonding. Uh, the theory is that it's as though all these electrons, these outer electrons that are not so tightly bound to the nucleus, they tend to form like a sea of electrons that are, ready to be moved around, right? And metals like copper, gold, silver, aluminum, and so on, these are called good conductors, right? And that's why if you were to go to the shop, the store, the hardware store, and you were to buy a piece of wire that you will use to, do some wiring in your house, most likely the core, if you want to go in there and peel it, right? Maybe I'll have to show you that. Very often, it's made of copper. Give me 1 second. Let me see if I can find a piece real quickly. It's not the best uh, piece I found here. Um, I don't seem to have a piece. Yeah, I have a piece. Give me 1 second. I'm virtually teaching, uh, in our workshop here. Yeah, let me just put on my camera for you. Look here. Can you see that?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, that's copper, right? Copper got this reddish look, right? Copper, most likely, and this is a piece of electrical wire. I was doing some wiring and this piece was extra. So most likely you will see that. If you were to, you know that wire that comes in from GPL to your house? What material do you think that is? Which metal is that? The wire that comes in from GPL. Hmm? As a matter of fact, all the wiring you see on the road. Huh? Which metal?
Sorry, is that copper?
The one that comes into your house from GPL and that you see on the posts outside run around the whole town, all over the world. You see it. Or what material is that? I'm asking you to make a guess. You almost know things, you know. You almost know things. That's why I'm asking you these questions. Somebody asks you, what metal is that? You know, what is that they use? And you say you go to Eugene, you don't know them things is. So we just identified copper is the one you use in the house. What is the one you use on that brings the power to the house?
I'm guessing it's aluminum. I'm not sure.
Yes, aluminum, right? It's good to get a piece in your hand one of these days. You see the workers on GPL grab a piece and feel it. It's very light, right? And it's much cheaper than copper, right? So that's why they have it there, run around the whole place. And um, if you know that aluminum is not, I know there's a word that they're calling it aluminum, right? Long ago, at least I don't know pronunciation. I would change in the spelling change so much. Yeah, anyway, it's not yeah. Um, Aluminum tend not to, corrode very much, right? There's a little coating of aluminum oxide, right? And that's it. It just forms on the surface, and that's it. But the rest of the metal inside remains, for many, 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 many years. Some of those power lines you see running on the road. I was probably not born yet when those were run. And they were there until today. Right? So they're aluminum, very, very good conductor. Used widely in the transmission of electrical power, right? Or electrical energy. There's our silver and gold here, right? You know where this is used a lot? These are used, gold, especially gold. Especially gold. I know where they're used. For good conduction. Any guesses?
Sir, as jewelry.
Oh, no. You don't want jewelry to be conducting electricity. In electronics, right? In your computer, right? All these electronics, especially so computers like processors and so on. The legs of the processor has some not the legs, the part that has to interface with the motherboard that would, long ago they used to have legs, but now they kind of, snap onto the motherboard. And that connection has to be, when I tell you, you can't have that corroding now. Because copper tends to corrode badly, right? Uh, I just told you that aluminum usually forms um, a coating, like, right, of aluminum oxide. Um, it might not be the best thing there because remember, your computer has to be, especially your processor, has to be reliable, right? When it comes to conducting electricity, right? So they use them a lot in electronics, especially your computer. As a matter of fact, I used to follow some people on YouTube where they would collect old computers and they'll remove the gold from them. They'll remove gold from the computer, right? Especially the processor and so. And they would accumulate it, and over time they'll sell it for, to people to make jewelry or whatever else. Yeah.
Daniel said his internet is unstable and he will not be able to move it to class.
All right. Yeah. Yeah. So then there are what we call insulators, right? These are, we should say bad conductors of electricity, right? And the reason why is because the kind of bonding, right, that is inside these materials, their electrons are bound to their nucleus very strongly, and they aren't easy to free these electrons and let them move around the substance, So they talk about some here, things like plastic, rubber, glass, ceramics, and so these are good insulators. As a matter of fact, that was ceramic. Sometimes they take a ceramic insulator and put on your wall, and the wire that comes from GPN passes through that, right? They kind of pass it through that, and then they take it into your house, right? My house, they put one up here. There's always a ceramic insulator there. Yeah. All right. So, as a matter of fact, the electric wire just showed you, there's a white coating over it, right? That's an insulator because if the wire inside is carrying current, and um, if you were to come into contact with a live wire, you can be shocked, right? You could suffer electric shock. So they usually put an insulator around it so that we aren't harmed, right? So they go hand in hand, right? You can't have one without the other, or else you can endanger your lives, right? So they all have their importance when it comes to electricity, using it safely, right? Then there are some other substances which we call semiconductors, right? And these, a couple, maybe 100 or 200 years ago, nobody cared about these, right? Nobody cared about semiconductor materials, such as silicon, right? Which is found in sand. You don't feel that's of no use. However, as time went by, and they're working on various devices like the transistor, which can become a switching device, and the diode and so on. These can actually be very useful in electronics in particular, and what we call semiconductor materials, right? Became very, very important. And that's how we have, all the fancy electronics we have today, the computer, for example, right? The chip inside, we call it the microprocessor, right? Is basically made of semiconductor material, basically silicon, right? And they call the process doping. they'll put in certain elements inside, and that would make it more conductive, you know, and they can now use it for various purposes, like the making of transistors, diodes, and the more complex ones you see, I will call integrated circuits, IC, in electronic devices. Right? So these are worth mentioning. We're not going to do much with them, but it's very, very important in the field of electronics, right? Well, so let's talk a little about electric charges, right? And we earlier talked about, you know, the structure of the atoms and how certain atoms in certain materials, and in particular I'm talking about conductors here, they tend to have a loose electron on each, you know, each atom that, or one or more, right? That are kind of free to move around, right? And kind of lend itself to having an electric current flowing through it. I know I'm using the term kind of premature. We haven't talked about what an electric current really is, but we can get to it, right? So because of the looseness of these electrons and their ability to flow around the material, well, you might have a material where there's a net negative charge or a net positive charge, right? That can happen. And sometimes in one material, one area can be made net negative, one can be net positive, right? And the result is that because of that difference in charge, you can have electrons flowing, right? Like you see, okay, look at the second diagram and the third one, right? Okay. So here, the net charge is negative, and over here, the net charge is positive. So the tendency, right? Let's say this is one single conductor, and one part of it is net negative, right? And the other part is net positive. What would happen, right? Once left alone, what would happen is that the electrons will tend to flow towards the positive charge, which is the nucleus, right? So that there's a kind of equalization, right? There's a kind of equalization. Like this second diagram, basically you have two electrons extra. They can go over here now and pair off with these two, while this one kind of pair with this one, right? So basically that's how you get an electric current really, right? So if I'm to go over here, electrons and protons actually behave very much. They behave very much like magnets, you know, like how magnets, North Pole is attracted to South Pole, right? Well, in the case of electric charges, there is that tendency of negative charges, the electrons tend to be attracted to the nucleus, right, which is net positive of an atom, right? And well, you know that if two electrons are by one another, they will tend to repel. Similarly, two positively charged nucleus, right? They'll tend to repel one another. What creates an electric current mostly is this attraction of negative to positive, right? Negative to positive. So once you have a situation in a conductor where there is an imbalance of charges, well, the conductor will eventually kind of balance out itself by letting the charge is flowing in a way that will neutralize the, the net negative or net positive condition that exists, right? And that is what really creates what we call an electric current, right? So there's this definition you hear very often, that electricity is the flow of electrons, right? So they kind of apply it or define electricity that way. Not that that's, that definition fits every time, no, right? But in the way we approach this subject here, we're going to call it, or we're going to refer to electricity as that flow of electrons in a conductor because of that imbalance of the charges inside, right? So they're telling you here that this flow of electrons, they want to measure it. They want to measure it, right? And how do we measure it? Well, we measure it in amps, right? Or amperes, right? I want you to write down somewhere in your book there, and I want you to hunt down the definition of how much is 1 ampere, right? I'll give you a hint. It's related to the charge of an electron, right? The charge of an electron is measured in something called coulombs, right? C-O-U-L-O-M-B, coulomb, right? And 1 ampere is a flow of a certain amount of charges from one place to another, right? But I'll allow you to do a bit of research. You never know, I can ask you that as one of the questions. To define the coulomb, but how much is 1 ampere, right? Ampere. And that's what current is measured in, right? Our current is measured in. I just want to clarify something with you. Let's say you have let me see if I can draw it here. You have a conductor, right? And you are to connect a battery to it, You connect a battery to it. So this side is positive, this side is negative. And it is not to say, and I think this is a common misconception, that when you connect the negative of the battery to this conductor, electrons are going to flow out of this battery into this conductor. Now, it is not to say that the electrons that come out of the battery here will travel, and reach till here out and go into the battery. No. Electrons do flow through. Eventually, that, yes, the one that came out of the battery could very well end up in the other side of the battery, and the positive side. And there's something called drift velocity, and so we're not going to get into all of that. But really what happens is that when a few electrons flow from the battery into the metal or the conductor, what happens is that creates an imbalance, right? So when the electrons flow here, it kind of repels other electrons, right? Which in turn repels another set here, which in turn repels another set, which in turn repels another set. And then lastly, some are repelled out of the conductor into the positive side of the battery, right? So it's not that the electron that came out of the battery will flow all the way and reach here, no, right? Some might eventually reach over time, but it's not that you need these electrons to actually reach here, no. These, the repelling effect goes on until some of the electrons here just repel out of the metal into the positive side of the battery. Right? Keep that in mind. Oh, I'm using the wrong eraser. Here. Yeah. So reference is made here to AC current. We're going to come to that a little later, right? But I just want to tell you that in AC current doesn't flow the way as in DC current. Like when you connect a battery to a conductor, you know, um, well, in that case, you have what we call direct current flow. But in AC current, like what you have in your homes, the GPL supplies, it doesn't involve really the flow of electrons so much as in the oscillation of electrons, right? Of the atoms inside of the material. It involves mostly the oscillation rather than the flow, right? So keep that little difference in mind. We're going to go to that in just a minute. And well, this little chart will tell you, you know, some multiples and so on, and submultiples of an ampere, right? And you'll get an idea of the size of it when you do some calculations in just a minute. Good. Now, there's something we want to clarify before we move on as to how current flows, right? What had happened before they understood how is it that electricity is being conducted along a conductor, right? Before they understood that, well, it's really electrons that are flowing. What had happened, you know, scientists who normally meet up and they'll make decisions as to, well, okay, they say, man, well, okay, if you're drawing a circuit diagram, you know, and we have a battery in the circuit diagram, we want to put how the current is flowing. How should we do it? And, you know, they're deciding that they will say that current flows from the positive side of the battery to the negative side, right? So they're reasoning, look, we have a circuit. So there's a battery here, you know, and there's a light bulb there, maybe, right? So, and the switch is closed, right? So let's put the switch there. So they said, look, and they agreed between themselves. Let's say current flows this way, right? Current, and the symbol with I, right? Current flows from positive to negative, right? And well, they think that the current flows this way, that way, right? Later on, they realized that, man, this was not the best thought, you know, conventions that we have adopted, because current is really the flow of electrons, and the electrons are flowing this way, right? It's flowing that way, right? However, they didn't change. They said, look, let's stick with current flowing from positive to negative. And that's why if you read circuit diagrams these days, you will see that the direction of current flow is still from positive to negative, even though current flow is basically the flow of electrons, right? So it seemed like a contradiction, but it was something, a decision that was made, and we just live with it today. So now what creates the flow of electrons? What creates that flow? Right? And what creates that flow is something called a potential difference. Right? A potential difference. And in layman's terms, what that is basically saying, and I think I illustrated it on there. You have a conductor, you can have a conductor, right? And what has happened is that whatever you know happens, and this conductor ends up where down here it maybe becomes net positive, and down here is net negative. What happens there is that you have created what we call a potential difference, right? A potential difference. And when a potential difference exists, well, then you would have that flow of electrons to kind of nullify that difference in potential, right? And really and truly, in most circuits, what creates a potential difference is an energy source, like a battery, right? Like a battery, as you see in the diagram. And batteries, you say that, well, because they have that ability to create a potential difference across various elements in a circle, like a bulb or a resistor, or, or something else. They say that it has what we call an electromotive force, EMF, right? So any uh, battery, that has the amount of that has some amount of energy can very well create what we call or have an electromotive force, an EMF, that can in turn create what we call a potential difference of various components or elements of a circuit. And you're gonna see that in some real circuits later on, right? So you see a little table here of some multiples and submultiples of the volt, right? Or the volt. So you have 1 kilovolt, you have millivolt as well. And just to give you an idea, like if you go into your remote, TV remote, that battery you see in there is usually around 1.5 volt, right? The car battery that you probably have in the car is about 12 volts, right? Oh, that sounds like my I have to get a charger for that. Give me a second. Can you all still hear me?
Yes, sir.
Oh, you hear me? Good. Yeah, my battery went down on my speaker. Yeah. So just to give you an idea, so your little battery in your remote would have about 1.5 volts. The car battery so will have 12 volts. You have 6 volts battery. You have those little square. Well, we say square battery, but it's more like what a cuboid shaped battery, the 9 volt. You see them. I'll bring my multi-tester in just a moment and show you how. It has a 9-volt battery inside, So you have an idea of, and then like your house. Your house runs off what we call AC voltage, but it's around 110, 120. Some places that 210 or 220 volts, right? When you get up to those large voltages, well, then you get to the point where you have to be very careful because you will suffer an electrical shock and die, right? So those medical people in the class, you almost research what size of current can kill you. Right? Can stop your heart. Have you ever seen somebody who gets shot? Anybody ever witnessed that? Have you ever been shot? Like
Yes, sir.
How does it feel?
Sir, it don't feel good.
Doesn't
It
feel
feel
good.
like it's left your whole body tingling.
Yes. As a matter of fact, if you have a good shock, your hands becomes immobile, and for a moment, this thing just paralyzes you. I actually witnessed a child near to me here. It's a big boy. He was not a child. He was probably a teenager. He's fooling around with some wires and got shot. He actually kind of piece on the wire piece on his hand. Anyway, his father broke through the fence. He was in another house nearby, building nearby. And well, this particular wire and dragged him out. He nearly died. Nearly died. So electricity is very useful, but it's very, very dangerous. I think that's as I used to work at the estate. I go in the electrical workshop. There's a big sign that says, what you can't see can kill you. But so let's talk some more about some components that you see in electrical circuits and their role and so right. Um, every electrical circuit will have some resistive elements inside, right? I have a lot of different elements you can see in a circuit. I was drawing some diagrams before. We're gonna have a battery that will create the EMF or the electromotive force in the whole circuit, right? And that is what would cause what we call voltage drops across various elements, right? That's an element of the circuit. The source of the EMF, the battery. You're talking about a switch. You can have a switch, just like you saw a light, right? And a light can be an example of a resistor or a resistive element in a circuit. Sometimes, though, there's a reason why they might want a certain voltage drop here so that they can do something in a circuit, and they actually put what we call a resistor, as you see in this diagram here. You can have a resistor in a circuit, right? Again, let me see if I can find a piece of equipment. Give me 1 second, I'm looking. Give me 1 second. Look here. This here is my charger, I'm an electric bike. As a matter of fact, you see a whole lot of different elements here, right? Let me give you some examples. Like down here, if you can see that, this little green thing here, that's a resistor. And they have copper well inside this circuit, right? They have copper intertwined to different resistors. Anything you see, like you see in the diagram, there is some stripes on them, right? Let's see if I can. Yeah, those are resistors. Then you have capacitors. You see these little green things there? These green things. There's a set of capacitors there. I have a whole lot of them, right? These here are capacitors as well. These are about ceramic capacitors. These are electrolytic capacitors. That's a transformer there. There's a transistor. Let me show you. There's a transistor hidden away. See there? There's a transistor in there. That's a transistor. Right? So yeah, that's a big capacitor. One big one. Right? Big capacitor. So those are different, so many different elements. There's a little fuse. I don't know if you can see that. Little, let me see if I can pinpoint it. That's a little fuse. Right? Yeah. Yeah. A frog went into this thing. A frog went in and caused it to catch a fire. So I have to go repair it. I have to get some diodes, 4 diodes I need to get it repaired. Yeah. So yeah, resistors are very common elements in a circuit. But as I said, not only resistors offer resistance in a circuit. As a matter, if you have a little bulb or a lamp, they call it, in a circuit, it would offer some resistance. Capacitors have a certain resistance. You have what you call inductors, little coils there. In a circuit, those are they have some amount of resistance. Every element almost have some resistance, right? But then sometimes you have an element in the circuit that you call a resistor, right? Because you put it deliberately there. And resistance is measured in ohms, right? I'll use my multi-testing just a moment. You'll see what it looks like now. You test the limits and all of that. Right? And the good thing I mentioned the word ohms just now. There's something called Ohm's law. Right? And this guy, there was somebody's name. So Ohm's law actually relate, the electromotive force to the current and the resistance in the circuit, right? And basically, you see it here, it's in the diagram. You see it, right? So, current, or V equal IR, right? Instead of V, sometimes you see E. I think that's what they use here. E equal IR. In other words, the current multiplied by the resistance, which should be equal to E, right, or V. And that is true of the whole circuit. You take it as a whole, or even if you were to just take a component within the circuit, right? The voltage across it would be equal to the current multiplied by the resistance, right? And basically, this formula captures what we refer to as Ohm's law. This is a simple example, right? So you have a 10-volt battery, right? 10 volts. There's a 5-ohm resistor, right? And they're telling you that there's 2 ampere flowing. Right? That comes from, remember, P equal IR, right? IR. So if the voltage is 10 and the current is 2, then the resistance would be 5, right? So you must multiply to give you the voltage. Right, that's what that is. So you would know that no circuit is that simple. Right? So in real circuits that you look in, they look in electronics and stuff. It's very complex. You have several resistors, right? So you have series resistors that are in series. You have resistors that are in parallel. You have resistors that are in series and parallel. There's a series, parallel or parallel series. So they're not easy, the electronics gets very complicated. So let's look at resistors in series first. What I mean is that the resistors are connected by the same current that flows through one, flows through all. Right? Look at an example here. So you have a number of resistors, 11 kilo ohm, 2 kilo ohm, and so on and so on and so on. Right? And I'm not seeing a voltage here. But anyway, we can come to examples where you're given a voltage so you can be able to calculate the requirements. But when you have resistors in series like you see here, the total resistance, right? The total resistance is just the sum of their R. That shouldn't be R. You just add them up, right? You add all of them. And the current through all those resistors is the same. So if you want to find the current, you just divide the EMF of the battery, whatever it is, right? Whatever it is, it's 12 volt, 6 volt, or whatever, divided by the total resistance I'm seeing 16,100 ohms or 16.1 kilo ohms. You just divide it by that, and you can actually find the value of I, right? And that current is the current that's flowing through all of those resistors. But there is only one path. There's only one path for the current, right? I mean, in this one here, it seems as though they put current flowing from negative to positive. You know, if you were to go with the convention, current is flowing through here from a battery is one value, I, right? I know they have I1, I2, I3, I4, I5, but you're obviously the same current that flows in here, flows out here, flows out here, flows out here, flows out. You know, one value because of there is only one path for it to flow. So let's take a little example here, right? So here's a little circuit. What you're seeing there is what we call multi-tester. They're all over now. I bought a very cheap one from the Chinese. About it, using it every day. So if you want to know the resistance across all these resistors, notice where the probes are placed, right? If you want to know the resistance between, or the resistance of this one resistor, notice where you place the probes, right? Notice where you place the probes. Again, maybe I should show you my little, give me a second. So let me show you my little gadget here. So this is my little multi-tester, right? So you take your, there's a little place here where you put the red, and you don't have to worry about that. It'll tell you, right? If you watch it good, tell you that you can measure voltage, resistance, current, and so on. You put red in there, right? And the black goes in. We have like a ORT. We have a ORT symbol, like the ORT symbol is something like this. That, you know, yeah. Sometimes they put com, meaning common, right? And you take these two probes, and if you want to find the resistance of, let's say, a piece of, okay, let me show you what's going on. So you have a little wire here, right? So you want to know the resistance from, oh my, I just broke my, the probe, oh my, I just broke my probe. That's why I'm getting some bad reviews on this thing. So you normally take on the one second. On this dial here, right here, there's a place where it measures resistance. And since the resistance of this piece of wire will be very small, I'll put it to the lowest, 200 ohms, right? And if I were to take this probe and put it on this wire like this, you put it like this, you put it like this, right? Put it like this. And it'll be a reading, right? It'll be a reading. This thing actually breaks, so I'm getting, it's not working. Like my probe just break. Just go. All the demonstration page. And maybe that's why I'm having so much difficulty with my readings as my solar panel gave of this one. Not this one, yesterday, in fact. And I was testing it, but it seems as though it was the probe that was the problem. And not the panel itself. Oh, yeah. Yeah. Okay. So you can use the multi-tester has everything in one. It's an ammeter, it's a voltmeter, it's a ohmmeter or resistance tester, all in one, everything. Actually, the one I have can test transistors as well. Let's take an example that involves some. Before we go to the example, yes. So besides series circuits, you have what we call parallel DC circuits as well, where the resistors are in parallel. Now here you're seeing that in parallel circuits, the current can take different paths. You see, the current can come here and it can pass through this resistor, right? And it can pass through this resistor. See, there are two different paths to the current. And if these two resistors are different in value, it will affect the size of the current. It will affect the size of the current, right? Now, even though we're talking here about DC circuits, I want to tell you that I will say most all of your circuits in your house are parallel circuits, right? So you have like I'm going to come to that in a second. You have a 110 volt, mains coming into your house. And every appliance, right? If we consider it like a resistor, they're all wired parallel, all your appliances in your house, right? So notice the total current here, I total, is the sum of these currents. So the more you add on appliances, the more that will be plus I4, plus I5, So the more you add on resistors here, the more you add on, the more the total current is going to become. And that's why they tell you the wire that comes into your house and the wire that is along the mains from which all your circuits are connected. You got to be very fat, right? You have to use, I think I have 10 mm wire. Let's not get into it, but you have to use a large, wire or a wire that can take a large current, Yeah. So how do you, the total current is just the sum of the currents, right? How do you calculate the total resistance in the circuit? Let's see. So this is the formula here. Total resistance, 1 over the total resistance is equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on, right? So to get the total resistance, you have to use this formula, right? You have to use that formula. We'll see an example or two here. Let's look at an example. Right, so, well, we're not going to have so many resistors, you know, we can just stick with about 2 or 3 of those. That's for you not to have too much mathematics. Right, so let's take this. You have 3 resistors in parallel. How do you calculate that? Well, you're going to use our formula, right? And that's it. It's 1 over 5 plus 1 over 10 plus 1 over 20. Right? So that is equal to 1 over R1. So we get our total, sorry. Our total then is 1 over that sum. Right? So you add up, but 1 over 5 is 4 over 20. 1 over 10 is 2 over 20. 1 over 20 is 1 over 20. So I guess I use the LCM of 20, right? And well, you will figure out the mathematics. So the total R1 over R total is really 7 over 20. So to get R total, you just flip this fraction, 7 over 20. You flip it over, you get 20%, which is around 2.86. Note, the effective resistance of these 3 resistors in parallel is actually smaller than the 3 with any one of these 3. You notice? You notice? Right? It's actually small. The effect of adding, 3 resistors in parallel is that you end up with a smaller resistor. Right? Keep that in mind. And that would mean that the current that is going to flow overall here is going to be very large. Right? Because it's small resistance overall. So look at another example. So you have a battery that is 10 volts. And you got 3 resistors in parallel. You want to know, the total current. You want to know the current in each branch, right? So across each resistor here is 10 volts, right? So to calculate the current in each branch, you have to divide 10 by 5. I'll give you 2. 10 by 10 will give you 1. 10 divided by 20 will give you half. So you add up all 3 of that and you know the total current. You know the current in each branch as well as you know the current overall that is flowing in the whole circuit, especially this part, that part. So let's see what happens. So the total current, notice they add them up, 3.5 ampere. You follow that? I'm not hearing anybody saying nothing.
Yes, sir.
Yes, sir.
So as I said, things can get very, very difficult, right? Where you have series, parallel, or something you say parallel, series circuits, right? So you have a combination of the two, right? So here, this one is in series, and this one is in series with this parallel pair, right? Look here. This one you have 2 in series, but these 2, right? These 2 who are in series is in parallel with this one. See? So you can have that. Right? You can have those combinations. And things get more complicated here. Let's see if we can do a calculation or 2. Okay. And what you're trying to do here is calculate, the overall resistance of each of the circuits, right? So here, what you'd actually have to do, look at this first one. This first one. You'd have to add these two in parallel first. That's what you're doing, right? And when you finish doing that, then you add this 5 ohms, right? See, step 2 here. So the effect of these two 10 ohms in parallel is 5 ohms. And then you add it to that 5, you get 10 overall. So it's like you take this circuit, you simplify it to this. See? Look at this one. Tell me if you're not following it. These two in series, you just add them just like the 5 and 5, 10. So down here becomes 10, and that is 10. So you add them like you add parallel resistance now, right? And you get 5. And then from that, if you were given the EMF of the battery, and so you can calculate the current in each branch, you can calculate the overall current in the circuit and so on. No?
So, sir, the sum of the parallel circuit, it's always equal to the sum of the series? Or you might have different values?
Where? Okay,
Sir,
this
the
one here?
sum. Yeah, I say that the sum is actually like the same to the series. When you add it, you get the parallel.
No. Every case will be different. These values were nice values they use so that the calculation comes out nicely. You have some horrible real life answers if you were to use different resistors here. The writer of this article actually use nice numbers, so that the calculation is not complex. But remember, all kinds of values you can have for those resistors, right? So you got to know your little bit of mathematics. Let's look at an example. So it's the same one as just now, where you put in some EMF, the battery voltage in each case, right? So they say using the same circuits that we had before. We're calculating current values now, right? Current values. So look here. So if you want to know the current in the overall circuit, you take these two, add them up, and we got 5. So that's 5, and this 5 will become 10. So the current in the circuit is 20 divided by 10, which will give us 2 ampere. Right? Simple enough. Let me ask you a question. If I want to know what is the voltage across this 5 ohm here, how will I figure that out? The whole battery. So let's blow this up some. Let's say I stick a voltmeter here. I stick a voltmeter. So let me go. I'm taking this. Yes, I'm taking this circuit, right? So I'm making it big. So I have this resistor here. Right? So if I were to put we calculated the current to be 2 ampere flowing here. So if I were to put a voltmeter there, you normally put it in parallel with this. What will this reading be? So keep in mind that this is a 5 ohm resistor. What will that voltmeter read? Anybody knows? Remember we said V equal IR. You know the current, you know the resistance. So the voltmeter is going to equal to 2 multiplied by 5 equal to 10. Right?
Yes, sir.
Right? And I mean 10 volts, right? So let me ask another question. These two are identical, right? This is 10 ohms. This is 10 ohms. What will the current here? This current here. And what will the current be? See if anybody is thinking. Keep in mind, 2 amperes is flowing here. 2 amperes from it pass through here. 2 amperes flowing here. What will the current here be, and what will the current here? This is 10 ohms. That is 10 ohms. So let's say you were to put what you call it, ammeter. Ammeter there. Ammeter there. What will it read? What will the ammeter read? A equal and it, huh? What will it be?
So are the ohms divided by the amperes?
No. All right, look at this. If these two resistors are the same, then this current is going to split in two. It's going to be 1 ampere. Right? Because the two resistors are equal. So the current will split equally. If they are not equal, then they wouldn't split equally. Right? If you want to know, or let's say they're not equal. Let's just see, right? Let's just see. This one was 5, and that one was 10. Right? Now, what you have to first figure out, the voltage across this one is 10. So the voltage across here, the remaining voltage will be 10 volts, right? So the current through these two branches now, if 10 volts is flowing, is across here, the current, let me just move this on the side. Yeah. Yeah. If this is 10 volts across this thing, so let me come on here. We got this here. Across here, or coming in here, is 2 ampere, right? This is 10 ohms. This is 5 ohms. Across here is 10 volts, right? The voltmeter said 10 volts. The current in here, what will the current in there be? What will the current in here? So if I were to put an ammeter here, what will the ammeter read? And if I were to put an ammeter here, what will it read? What will it read? Use this relationship, V equal IR. So I is going to equal to V over R, right? So what will this one read?
It'll be 1, sir.
1, right? And what will this, oh, well, that would mean, right, if this happens, this 2 amp wouldn't be right here, right? It'll change the whole problem. So, but if we found out that 10 volts is across here, right, we just say, right? 1 ampere there. And this one will read What will this one read?
2
5.
amperes.
How much?
2.
2 ampere, yeah. So the overall flow here will be 3 ampere and not 2. Right? So that's how you make use of Ohm's law and this whole part and the series thing and so. I'll give you some questions so you can try and you're going to present them as a tutorial later on, right? Yeah. Let's talk about power in a DC circuit now. Power. Right? Power. So there's a relationship P equal IV, right? So remember, instead of V, they use E, right? And remember V equal IR. So if you put that back, IR in the place of V, you get P equal I square R, right? So these are the two relationships here. Power in a circuit is equal to the current by the voltage, or square of the current by the resistance. Right? Those two. You actually can use that to calculate. As a matter of fact, these two formulas, right? You can use to calculate the power of appliances in your house use. Usually, though, I want to tell you that your appliances will normally have a label that tells you its power, right? Usually, you want to calculate how much current is going to flow so that you can know what size wiring. Like the people tell you, look, if you have an air conditioner, you have to have the wiring has to be fatter than if you're running a light, right? And people are more interested in the size of the current that will flow in a conductor. I'm not saying you're not interested in power. Before we move on from power, what we might want to calculate is what we call how much energy an appliance uses. And remember, power is equals to energy divided by time. So energy will be power multiplied by time, right? Which is volts by, or VIT, that's how I remember it, volt by current by time, right? If you have an appliance in your house and it's rated like an iron, right? Let's say you have an iron. The iron is 1,000 watts, right? 1,000 watts. You're using this iron for 1 hour. Today, use it for 1 hour. So the energy that you use will be 1,000 watts multiplied by 1 hour, right? So this is equals to 1,000 watt hour. Usually GPL sells you power in what we call kilowatt hour, which is equal to 1 kilowatt hour, right? And 1 kilowatt hour, I think, is roughly around 55 cents or 50 cents thereabout. No, sorry, $55, right? Not 55 cents. Where did I get that from? Nothing sell for cents in this country. So if you iron for 1 hour this morning, you use around $50. You get it? If you use your iron for 2 hours, you have to pay GPL about $100, right? But once you know the power of the appliance, change it to kilowatt and multiply by the amount of hours that you use it for, right? You can calculate how much energy you use in your house. So this is an example of calculating power in a DC circuit, right? So you have a 12-volt supply, you have a 6 ohm resistance, right? You calculate I using E over R, 2 amperes. And from that, you can calculate power, right? P equal, they use different formulas. three different ways, right? 24 watts. So let's talk a little about alternating current. And there's a main difference here in that when we talk about direct current, we're talking about the flow of electrons in a particular direction through a conductor. But with alternating current, what happens is that electrons are not flowing, from one end of the conductor to the other. No. What is actually happening is there's an oscillation, right, within the conductor, right? And the oscillation actually has a waveform that is very similar to what we call the sine wave, right? And this is what it looks like. So a little right up here about alternating current, right? And they're explaining that with direct current, electrons are flowing continuously in one direction, right, from the source. However, in the case of the AC current, there's an oscillation or a to and fro movement of electrons. It moves in one direction and moves back in another direction, right? And this is because of what happens in the generator, right? The AC generator. There's a reversal. It's like, okay, when you have a direct current circuit, right? So you have a battery. And so there's a resistance there. So the current flows like that, right? One direction. But with an AC here, AC, what happens with this generator is that it changes polarity. Plus, minus, then it switches around. Minus, plus. And it does this as often as like in our system that we have. It does it 60 times. That's why they say we experience or we have what we call a 60 hertz supply of electricity to our houses, right? Most countries like England, most of Europe and so, they use 50 hertz. Here in the Caribbean and like in the States and so, we use 60 hertz, right? So it has to do with how fast the polarity of the generator changes. And I'll show you in a moment what I'm talking about. Right? It changes in 1 second, 60 times the polarity changes. So let me just let's see if I can get this is a nice diagram here. So look here. So when this rotor here, there's some coils. So here's a magnet, there's a magnet, right? So these coils that you see here are going to spin in this magnetic field. And what they're saying is that it will spin 60 times in 1 second. And I guess you see generators, how fast they spin, right? So they spin fast in 1 second, 60 times they spin, right? And that's what creates what we call the 60 hertz power supply that we have, right? Usually when you're buying appliances, you must watch and read that it's a 60 hertz. If it's 50, you might have some humming. I don't know if you have any appliance at your home that hums, right? Because that humming comes really from sometimes a difference. Not always. There's some other reasons for humming. Sometimes it's because of the frequency differences, right? Yeah. So here's a little drawing of the 60 hertz, What are you telling me? 15 cycles in a quarter of a second or 60 cycles in 1 second. And a lot of speed, right? A little waveform here, right? So sometimes people would argue that, look, why if this electron oscillates up there, comes back to zero, and then go down here, why the average value is not zero, right? But when we measure, like when you measure your power supply, you get what we call, let's say 110. 110 volt is what we call the root mean square value. Root mean square, the RMS. And it's usually, if you notice here, it's 0.707 of the peak value. So your alternator that you have in your GPL might be producing more than 110, but the root mean square value is as though you take this part and put it up there. And the root mean square value is the value RMS, right? And this is your 110 volts or your 220 volts, right? So this value is going to be a little higher. You can do the calculation because what you're telling you, the peak voltage times 0.707 is what gives you the 110. If you want to know the peak, you can always calculate. Right? And that's your AC current. We don't want to dwell too much on AC current. That's a whole big, even DC current, we haven't even scratched the surface yet. But this is just a brief, as I said, a brief introduction to DC circuits and a little bit of what AC current really involves, you know? Yeah. So we're telling you, you know, we're not concerned about the instantaneous value. We're more interested in the root mean square value, which is the 110 volts or the 220 volts that we get in our houses, right? I think that ends it.